At this point, we hopefully have our applications tuned. We've profiled them. We found the hot routines, optimized the loops, got it so that the compiler can vectorize them, make them parallel, and also dealt with communication overhead, the SGI MPI progress type of routine, and also an Intel MPI barrier type of problem, and also dealt with the scalability false cache sharing problems. The next step you really need to do with your application is to lock it down, privatize it, protect it from anything else. So that each thread, each rank gets its own private CPU, or even better, each gets its private core with no interference or noise coming from anything. When you start doing multi-threading, these threads can get locked up as a group. All you have to do is hit one or two of them, and the entire thread group gets into a problem. So there are a lot of times that application seems to get stuck, is in what some people call the bad state. The application might normally run for an hour, but now it's 3 hours into the run. You can attach to it with perf and see that it's either stuck in a barrier or what other kind of subroutines or kernel code is running there. So this module, I need to talk about DPlace and cpuset. That's the key thing here. So to get high performance, reproducible performance, I haven't done this yet, but that 9-second code 2, I can overcommit the machine and get that 9 seconds up to 40 or 50 seconds. Typically, even just going, I need to do this tomorrow, going to the other blade in the system, my 9 seconds will go to 13 or 14 seconds just due to NUMA latency. So to get reproducible performance, I need to lock things down and privatize them and keep all their memory references on socket, on node. So one of the key things we have is cpusets. We have PBS installed, and that is using a SGI library called libcpuset. I want to share my desktop here for a second. I'm going to do this on Mike's system for you, Mike, just to get it out of the way. I don't know if Floyd 2 and Floyd 3 have PBS actually installed or anything yet, so. So the daemon that's running, if I do an MD5 sum on mom, the default PBS mom is the standard PBS mom. I'm going to do a service PBS stop. And then I want to copy. Some people will link, but I'm just going to do a copy here. Let's see what they got here. So here it is a copy, not a link as well. But I have seen it a link instead of a copy. Now, before I do this, ls on dev cpuset, there are no cpusets other than the root or global cpuset. Now that I've got that new mom in place, and Mike, this is what I had to deal with yesterday or whatever to get your license in place so I could get a clean startup for the license and when it expires. Now if I do an ls on dev cpuset, I now have a PBS Pro cpuset out there. There are no jobs in it yet. Let me submit a job here. Code to MP. Let's try this one here. So while that's running /dev/cpuset/PBS, I then have a cpuset just for that job. I'm going to try this cpuset-capital. Oh, I don't know that I have it here. I have a cpuset-Q. Oh, job is done. Maybe it isn't. It's still running. Let's see what top says. It's done anyways. Let me come back to that. But I have a cpuset-Q. Let me try this again here. VI25 splat. Let me come back to it. I wanted to look at the affinity information in the cpuset that got created. Well, let's get back to the presentation. So PBS, as far as I know, Torque was last time I saw it was still using shell scripting to create the cpusets, not libcpuset, but I don't know that for sure. TapSet is a way of pinning a process to a specific CPU, also to get the affinity for a process. And I got to get into NUMACTL tomorrow and show the effect of NUMA latency going across the interconnect. Then I got to get into DPlace, DLook, and there is being added a DLook summary command. I want to use that tomorrow. And again, I have my own little script called cpuset-Q that will run a PS on every thread in a cpuset. You just list the cpuset name. It'll run a PS on it. It'll run a DLook summary on it, and it'll also grab the affinity mask. But I'm going to demonstrate that tomorrow. There's also a library interface for applications to come in and do their CPU and memory placement. Now, in order for DPlace and DLook to work, there is an SGI kernel module known as NUMA Tools that has to be loaded. And that is usually for SLES in the itsysysconfig kernel file. Again, OMPlace is a wrapper to DPlace, and that's primarily meant for MPI OpenMP hybrid. DLook will actually look at my page table for the process and show me where the page got placed. Now I can spot swapped pages. I can do DLook and grep for uppercase swap to see if it's got pages swapped, things of that sort. So here I've got a DLook example, and then I can see the node here. Number of pages on that node. So TapSet is normally working on a hex bitmap. In the workbook, I put a hex to binary bitmap example for you. So if I have a 1, that would be CPU 0, a 3 with CPUs 4 and 5, and then the other one was CPU 8. Now, I always thought this strange. I don't like the syntax here, but -P says do it on a PID. But the order is sensitive. I do the -P, then the bit mask, then the PID, which I always thought was strange. And again, with that bit mask, an 8 was CPUs 3, and then the A was CPUs 5 and 7. I can also do it by CPU number. And a taskset-P with a PID just gets me my affinity mask. I'm going to share my desktop here for a second. So let me try doing a taskset-P. Let's just do 0x1. Now, before we do that, let's do it on my current PID. So I have an affinity mask that looks like that. I'm going to cat slash, or let me do a tail. Tail /proc $$ /status. And now I can see the affinity mask both as a mask and as CPU numbers. So in my cpuset-Q script, I'm grabbing this stuff as well as the taskset information. So now let me try changing my affinity here, -P 0x. Let me just go 1. So now it says my affinity mask is a 1 instead of all the F's. And let's just check here. Shows a 1. And when I look at this one now, I can see the only memory I'm allowed is CPU 0, which is the 1 bit. Okay? Now, everything that I run should have affinity and inherit the affinity that I currently have. Let me put that in the background. Let me bring up top. Let me go to an F. Let me get rid of priority. That's useless. Let me get rid of share. That's useless. Let me add the CPU with a J. And let me get the WChan event and end faults. Go back and what we got here. Oops. And I can see that I'm on CPU 0 here. Let me try a taskset on that thing. First of all, what's the PID? So now a taskset -P0x, let me go 4. So 1, 2, 4, that'd be CPU 2. And then the PID was 26306. So now if I do my task set on that thing, wherever it is, let me just grab it here. 26306. I now see I'm on affinity mask of 4. And that is actually CPU 2. Bring up top. Oh, I guess I didn't save everything. Let me do the F again, get rid of the priority, get rid of the share, add in the CPU, add in end faults. Let me do a Shift W to save that thing this time. Okay, program looks like it finished. Let me run it again. PS- let me do a task set -P0x4. That's where we were on PID 26427. Now let me tail. And there we can see the CPU it's on. Bring up top. There's the CPU. It's on CPU 2. Now, if I do a PS-L, nothing. This has nothing to do with anything. These are completely garbage here. But if I do an export PS_personality equals IRIX, do a PS-L, I can see a CPU if it's running. If it's sleeping, it's an asterisk. I don't like that. But here I can see it's running on CPU 2. Now, if I do a top-B, type into, actually number samples -N1, type into more, top will always give me the CPU that it's running on, even if it's not running at the time. Let me do a top here. Let me get the I out of there, Shift W. You can see the CPU will always be showing there with the top command. So some people will do a top-B script to kind of look at things. You have to be careful, however. One sample is not enough to stabilize the data. So when you're doing a top, I did a -N1, you should really do a -N2, but then there's no way to throw away the first sample. First time I bring up top, there's no guarantee that it's a smooth interval. Okay. Let me go back to the workbook. So I was just playing around with the affinity mask there. Then we have DPlace. Now, TapSet was Linux community. DPlace is SGI specific. Unfortunately, DPlace is not like it is in IRIX. It will only deal with CPU and not memory. I had asked that DPlace do memory as well, but they didn't want to do that, and they tell you to use NUMACTL instead. So when I do a memory allocation, default allocation is first touch. the node that I'm on. But then if I get bounced to a different socket, I'm now going across the interconnect to get to my data. So DPlace will bind my processes to a specific logical CPU within a CPU set. Now the whole purpose here is to pin me down to prevent migration or thread hopping. Again, I have to know the application. And my next slide is an example here. I talked about this earlier. I'm in Bash, and let's say I'm running a OpenMP application, so the program code2mp is going to spawn a libguide and then the other 4 shepherds. So if I had OMP num threads to a 4, I actually get 5 threads. And if I pin this to CPU 1, 2, 3, 4, this one will go back to 1. Now, if my program actually did something else, there is a library called known as system. Maybe the program did a system ls, which resulted in a child being forked off, and that's the second one. Then this is the 3rd, 4th, 5th, and 6th. In that case, this would go to CPU 1, 2, 3, 4, 1, 2. Now I've got 2 threads banging against these 2 threads. So you need to know the skip pattern. So if I've got 2 of these things, the 2nd and the 3rd thread are shepherds, then I want to skip them. I do not want them pinned. I've got to leave the demo of this for tomorrow. But normally with just 1 worker thread, we skip that 2nd thread as a bit mask. And then we get this pinned to CPU 1, skip it, 2, 3, and 4. And then we're back to 1. By the way, my cpuset command, cpuset-q thing that I had, is trying to show the affinity so you can actually see the affinity bitmap skew as it goes CPUs 1, 2, 3, 4, actually 1, skip, 2, 3, 4, or 1, all of them, 2, 3, 4. So DPlace, we can use the C, which is the relative CPU in the CPU set. We can do an N to say skip a number of procs before you start placement. We can do exact placement by name. We can place only processes with name. The main one was the skip mask. We can also do a placement file. OMPlace will create a placement file for DPlace. And there's also something DPlace can do called replicate shared text. If I'm 1,024 threads wide or worse, 4096, I don't want to be going across the interconnect to get to a shared text like a square root function or something. The interconnect gets busy from that, and if the interconnect is busy from something else, it takes time to get that shared text onto my CPU if the interconnect has high contention on it. So the -R will replicate the shared text on my node, and then I don't have to go across the interconnect to get to that DSO, that library or something. This was primarily used in the weather market in the past. So a couple examples, DPlace-C put dates on CPU 4. They do start with 0, which confuses people. How do I know what CPUs and stuff? 2 things. Let me go back, share my desktop. If I do a CPU map, which is part of the accelerate RPM or accelerate distribution, I can then see what CPUs are on a particular blade or hub, and we're starting at 0. Also, if I do a more on var run CPU node map, that can tell me what node a given CPU is on to kind of map these things out. So the CPU map command tells me what my interleave pattern would be like, and maybe I don't want the virtuals, and maybe I'm going to pin myself on 0 through 3, 4 through 7, 8 through 11, and 12 through 15, and not even touch the virtuals. And the parentheses tell me that those are the same core, sharing, instruction pipes, functional units, caches, and things of that sort. So anyway, second example here, I'm doing a DPlace and then skipping the first master thread, which is the MPI run command. The other one, and this is critical, I need to demonstrate this tomorrow. When I use DPlace, I got to disable KMP affinity. If I don't, they will end up on the same CPU. Let me get rid of this. if they're all on the same CPU, false cache sharing goes away, but you're still severely degraded. Not all of them are running concurrently. You got barrier problems, things like that. Now, in this example, I did a DPlace-X, and then I picked 0 through 7 and 32 through 39. But if I am in a PBS CPU set information situation, I don't need to worry about the virtuals versus the physicals. These would be logical within the CPU set. So this is not a good example in a CPU set example unless I'm trying to get a skip pattern to avoid sockets. Maybe on a UV1, I've got 2 sockets on the same QPI, and one of them is creating contention with the other, so I only pin to 1 socket. So CPU map gives you that spread pattern. I'm also running a DLOOK on a.out. And then showing a DPlace placement file. Here, any program forked that has the name GMPI and they're on CPU 0 will get moved to these other CPUs. So it's just trying to show some fancier ways of doing things by name. And then we have the OMPlace command. Now, OMPlace sets hard codes, OMP_num_threads, and also the KMP Affinity, so you don't have to worry about them. Recently, and I'll have to see what I see tomorrow, when I run the Intel OpenMP with the version that I've got right now, it looks at the number of CPUs on the system, not the numbers of CPUs in the CPU set, to determine how many threads to spawn. That's bad. So I'm on a 64 CPU system. I try to get 4 threads. I tell PBS to give me 4 CPUs in a socket, but then I'm spawning off 64 threads to deal with it. Now I've got sched yield, thrash, and barrier synchronization, high system time problems. So OMPlace will automatically set OM_num threads to what's in the CPU set rather than the number of CPUs on the system. And we also have to disable KMP Affinity for DPlace to work correctly. So OMPlace does all the same things. So they've got an example here with different thread counts for different CPUs and also the number of threads for OpenMP. So we can do MPI and OpenM3 and specify how I'm going to place everything. If I were out at site, I'd probably try to migrate people to use OMPlace rather than DPlace. The other thing we have is NUMACTL. I'm going to demonstrate this tomorrow. The default allocation is first touch, unless we're talking about the slab or the page cache. Those depend upon the dev CPU set spread parameters. If those are a 0, it's first touch. If they're 1, then all your file system I/O, I should say all your cached file system I/O, and all your slab will be spread round robin across the nodes in your CPU set. And with slash 11 and higher, they can be relative and CPU set aware. There is something in NUMACTL called relative distance. These are not clock periods or anything like that. This is simply a normalized relative number to see what kind of latency impact there is, but this is not any sort of time unit or clock periods, nothing like that. When the kernel boots, it kind of does a ping-pong test and determines an average latency to build a distance chart, a relative distance between the CPUs in the system. By the way, all that data is coming out of the prox devices system node number files. Now, it is important to have affinity. In the graphics market, they are using the topology command to find what blade or where a GPU is installed. And then from that, figure out where they want to get pinned, and then with NUMACTL binding themselves to where, for example, in this case, the HBA is. And again, nowadays, XVM is affinity aware and will find the closest HBA. but this is an example where we're trying to get affinity to a particular peripheral that topology says where it is. Everything is affinity critical here. Lock it down, leave it alone. Okay, I want to come back to node info, but node info is showing me on a per node basis, physical memory on the node, how much is free, how much is used. And again, we've been through this: dirty for write traffic, anon for process space, slab for the kernel. I have a newer version that has ShimM in there as well. The ShimM is really important for me because somebody else could come along, create a dev ShimM file, or do IPS ShimM, all of it allocated on that particular socket or blade. Job goes away, does not clean up. PBS gives me that blade, but now I have stuff on the blade that hasn't been cleaned up. So being able to see ShimM consumption, and by default, the ShimM is first touch. Let me share my desktop here for a second. If I do a man on mount, ShimM has an FS tab mount option called MPOL. The default is to do local node. So I do know sites that do an interleave instead of a local node. Now, what's the advantage and the disadvantage? The interleave is going to spread myself across all the nodes in the cpuset, or I could specify a particular node list, but that's going to increase latency to get to that stuff, particularly if what I'm dealing with fits on the file, fits on the node, fits on the socket. However, the interleave has the advantage of spreading that memory pressure around across the nodes. Then when I come in and try to use the node, it's not all on one node, it's been spread around, and then I don't have as much work to trim. So the interleave can be used to basically spread out the memory pressure impact you have from your dev ShimM files, but you do have a possible penalty because of higher latency for it. So again, dev ShimM is first touch by default. And if somebody's leaving dev ShimM files around, I might consider doing an interleave. Same thing if I am in a cpuset and I initialize a file in dev ShimM, it might be first touch, and then when I process it later, it might not be affinity aware. So again, that's another case where I might want to interleave. So if anybody's interested, I have a script in the guest bin directory called ninfo that has the ShimM information added in there. After that, then we have the allocation. Now, node info is not telling me about references, only telling me about the allocation. I can zero out and allocate the file and then go back later and, you know, read, write, read two items from memory and then write them off to a third one. But if it's already been initialized and pre-allocated, I won't see those references as I'm walking through the data. Kind of wish I had gmem usage from IRIX that would actually show me the stride patterns as it's walking through the data. So the allocations only occur during the initialization of the array, the first time it's referenced when it goes from reservation to allocation. And a miss says I could not find memory on my node, so I had to go off node. Miss, preferred node was full. I'm sorry, so allocation occurred on this node. And then foreign said the preferred node was full, had to allocate somewhere else. So if my node fills up, and these all have a lot free, but if my node fills up, then I'm going to get a foreign that's going to result in a miss coming in on a different node. Now that in general could be bad because now I'm off node. But that doesn't guarantee that later when I'm multi-threading that the multi-threading pattern is the same. And this is, again, where I go back, if I still have it here, going back to this. trying to get an interleave pattern in my memory references. So this is only on the allocation. And if I use NUMACTL with the -I, then I can get an interleave pattern and see that one. I'm going to wrap up here. So the last thing are cpusets. Now, cpusets originally were called psets in Solaris and Sun. Back in the 90s, when SGI implemented the Origin product line, they renamed the feature a cpuset, meaning that it dealt with both CPU and memory. And this was relevant for a NUMA machine compared to the old Spark systems that were not NUMA. So that got implemented in SGI, and eventually the Linux community accepted that interface since the 2.6.12 kernel. There is still a couple of pieces that are SGI proprietary, and we also have some newer libraries. There's a libcpuset library. There's a libbitmask library. The libbitmask does the mapping between the bitmask for the CPU number and the actual CPU number. So there are a couple of things that are still SGI proprietary. You don't need them to do cpusets, though. I know sites that have torque and are not using any SGI packages. Now, the cpuset concept is a file system hierarchy, a nested hierarchy. A little bit ago with my demo, I had a dev cpuset for the root cpuset. Underneath that, I had a PBS Pro cpuset, and underneath that, I had a cpuset for the job. One of the things you don't want to do, though, is overlap CPU sets. That's real bad. So I had a site saying, well, I don't want to waste these CPUs. Let's overlap the CPU sets so that we don't waste stuff. But that created contention between the work in the CPU sets. Yes, CPU utilization might have gone up, but that's because NUMA link contention went up, latency went up, and my throughput went down. That's the thing you got to really be aware of these days. With a cache-based machine, as I drive my CPU utilization up, that doesn't mean it's productive. My throughput can start going down because now I'm taking cache misses, TOB misses, barrier problems, fighting with noise in the system, all because my CPUs are at 100% utilization. So don't think that just because a CPU is busy, meaning that it's productive. Okay? Now, when you loaded SGI's foundation distribution, I think it's about, I think it was the cpuset package. When it got loaded, it added into the ITSI FS tab a line that mounted dev cpuset. So if I'm not using foundation, I would do that by hand. Again, cpusets can be subsets of cpusets. It's the permissions that determine who can get into a cpuset. By default, PBS Pro is creating these cpusets as root, which means the user can't go in and make changes to the attributes of the cpuset. For example, the spread parameters. So I know of some sites that have had a set UID type of program that can go in and change the spread flags on a cpuset. Now, the cpuset command is completely different from what we had in ProPack days. And also, there's no cpuset-q report, which is why I created my own. 3 ways of manipulating cpusets. One is by file system. That's the way I saw Torque doing it about 5 years ago. The other way is by a library interface or by the cpuset command. Now, in lab, you're going to do the first one and the third one. All cpuset names begin with /. If it's just /, that's called the root cpuset. That's the entire system. I also refer to it as the global cpuset or the top cpuset. So here I've got dev cpuset. Underneath that, I'm going to create a boot cpuset. Then I'm going to have an SSHD login cpuset. I might have a static cpuset to throw all my IO bound jobs in. So they say, if I'm not CPU bound, if I'm IO bound, why waste the CPUs? Let's just throw these things into the same CPU set. Or maybe it's a low pry queue. And then under cpuset PBS Pro, I'm going to have one per job. So the cpuset command is a way of creating them. C to create, M to modify, X to delete it or get rid of it. -D to dump the attributes. I can run something in it, but by the way, the -I does not handle arguments to the script command. I can't quote it or anything like that. It doesn't know how to parse a fancy command line, so I always put it into a script if I'm going to do that. I can list the PIDs in a cpuset. I can put a PID into a cpuset, or list the cpuset a PID is in. And I can do this by file. I'm going to demonstrate this tomorrow. Now, in the dev cpuset directory, we have various configuration parameters. The first one is called CPU exclusive. CPU exclusive, let me back up a second. A cpuset fences me in. I cannot break out of my cpuset. If I get node 2 and CPU 16 through 20 or something, 16 through 20, I cannot break out of that cpuset. So the cpuset keeps me contained. But other things can come into my cpuset if they're not contained in a cpuset. So if I log in as root or something, I might be able to break into that cpuset. So an exclusive simply says, this is my private stuff. Nobody can come in. This is locking the door so that nobody can come in. Putting up the cpuset locked the door so that I can't get out. So I've been imprisoned in that cpuset. But exclusive says the door is locked such that nobody can come into my cpuset. Then we've got the CPUs that are in the cpuset. You're always trying to group these on node boundaries or blade boundaries. So PBS Pro is smart enough to look at the topology command and to figure out how to partition or carve things out and grab the physical and the virtual that are on that blade. We also have mem exclusive that says nobody can come into my memory. So that keeps everybody out of my memory, reducing memory contention. Now there is one for slab and page cache. That does not work. A hard wall 0 says my slab and my page cache can go outside my CPU set. That does not happen. Mem hard wall is acting and behaving like a 1. Now personally I prefer that. I don't want somebody else in some other CPU set to write a 100 gig file and all that dirty data to slop into my CPU set, sucking up my memory. That would be bad. So even though it's working and is hard-walled, but configured to be soft and not containing the slab and the page cache, that behavior is not working. I do have the ability to move a node from one node to another. PBS Pro uses this for job preemption. Job preemption. I've got my job running. Mike submits a job. He's more important than me. So PBS Pro will preempt my job, suspend me with a signal for the suspend stuff, the pause. That will put it in a T state. And then it will move all of my work from the nodes that it's giving to the other job and then put that job on that particular CPU set or nodes. Another one being used, memory pressure. The number one way this is being used is to avoid out-of-memory killers. The problem with an is there's no guarantee it's going to kill the right thing. Also, I want to solve the problem before I hit So sites have a daemon up and running that, first of all, we have to enable it, and then any CPU set that is swapping will get a memory pressure value in it. Now, the notes will tell you the description. It's kind of like an intensity. If memory pressure is 0, there's no swapping. So what this daemon is doing is looking for CPU sets that have memory pressure occurring, and then we'll go in and kill them and kill the job before the operating system has to do anything. And this kill daemon is coded at the site to say, go ahead and kill Dave Wright, but don't kill Mike Harvey, and get some of the politics correct. And this will also prevent things like SOHOG-D or things like that from being killed. Now, the current kernel, when it kills, it finds the candidate from the badness, and then stays within that CPU set to kill things. Okay? So I've got a program, it's big in a CPU set, I go in and kill that thing, but that doesn't mean that I freed up its memory. I might still be in an situation because when I killed it, I did not clean up ShimM. Okay? Now the daemon comes in and starts killing everything else in the CPU set, but it's not freeing up memory because it did not trim, reclaim, or remove the unattached shared memory segments. Now, I've complained about this in the past, and the Linux community does not want the killer going in and removing stuff. They say it's up to the application. My problem is if I kill a process, I should remove its unattached shared memory segments. I can get the system so wedged I can't even shut it down. A dev ShimM can only take half my memory, but the IPCS ShimM can take all of my memory and all of my swap, push me to kills the process that had all that ShimM. The ShimM never got released, and now the killer is going to start going into the boot CPU set and start killing shutdown daemons and everything. So anyway, using memory pressure to have a site-specific daemon running that looks for pressure and makes kill decisions based upon that is more efficient and more politically correct than trusting the out-of-memory killer from the kernel. I always compare the killer as like, I'm glad the police don't just shoot randomly when someone's speeding. I don't want random kills for a violation on the road. Anyway, we have to turn that pressure on with the enabled. That is inherited to all children. There's only one pressure enabled at the top root CPU set. And if that is a 1, then memory pressure will have a value in it if there's swapping going on. I also have the spread page and spread slab. Those are to spread round robin my page cache, my dirties, my writebacks, my NFS, all that stuff in the page cache will get spread round robin within my CPU set. Sometimes I want that, sometimes I don't. The original reason to set these to a spread was small memory on an Itanium system, application comes along, reads a file in single-threaded, fills up the node with that file, and then starts allocating memory to deal with and process that file, and in the process starts trimming everything it just read in. So you get into this allocate, trim, allocate, trim, allocate, trim. I should say read file in, allocate, trim. Read the file back in, allocate, trim. That's kind of a page cache thrash, what I call an upside-down cache. My cache isn't able to hold the data because I keep trimming it. Now I have more physical I/O requests than logical because I got to keep going back to the file system for the file I just read in. But it got thrown away. So by doing a spread that reduced the memory pressure, spread it out across the nodes in the CPU set, now when I read the file in, it's spread across everything. And now when I have to grow and trim, I'm not throwing everything that's on one node. Same thing with the slab, to spread the slab around. We okay with that? Again, first touch versus round robin. If my assets fit, we can turn this stuff off. I got database Oracle systems and stuff that turn this stuff off. And they can hold their dev ShimM and their application on a node. It even figures out how much memory is on the node and then allocates ShimM just for what's on that node. We have another one here that specifies the memory nodes that are in the CPU set. And again, the var run CPU node map can help. The rest of these I don't really deal with. You can run a script when CPU set is done. So this says run it, and then here's the script to run on a release. And there's some controls about the load balancer. We don't really play with those. We just use DPlace and turn off the scheduler. And then the key thing is the task file contains the PIDs that are in the CPU set. So I went into dev CPU set. Now I already had a CPU set test command, file there. This is personal preference for naming convention. I have sites at times, and they don't know how their cpusets are being created, and I wanted to teach a common sense method of naming it such that you always have cpuset first, so I can do an ls on ITSE cpuset asterisk and see the configuration files. But it could be anything you want. So in there, this example put 2 through 5 and 7 just to show you can use a dash for contiguous CPUs and a comma for a break. And then memories 1 through 3. Then I did a cpuset-c to create a /test cpuset using that file. Then I did an ls, and where was it here? Test, created right there. Now when that cpuset was created, it is automatically populated with all these different files. So in this example, I chmoded permission for users to see it, CD'd into it, did an ls to show that it was already populated with stuff, catted one of the files to see that it had stuff in it. Then I ran my program in that cpuset, and while it was running, it's not clear here, but while it was running, I catted the task. Again, this thing might still be running, so I should probably really have an ampersand sign here. Then I could see what PIDs were in that cpuset. By the way, if I am logging in on the serial console as root, the first thing I like to do is echo $$ into the root cpuset so that I don't have any memory pressure and my interactive user login can go anywhere in the system. If I have a memory pressure problem in the boot cpuset and I log in through the serial console, and maybe on my prior serial console login I did something that left my node, my boot cpuset node full from dev ShimM or something, I'm in trouble. I'm memory starved. So, and I kind of wish I had a script to put the MindGetty thing into a cpuset, so that if I come in from MindGetty, I am not restricted to the boot cpuset. Now, most people have well-behaved cpusets, and that's not a problem. One of the things I do wrong, or a site might do wrong, is might put a boot cpuset and a SSHD login cpuset, different CPUs, but sharing the memory. Okay, so that could be a problem. Anyway, besides using the cpuset command, I went into the dev cpuset, did a maker, chmoded, CD'd into the directory, chmoded the task file for permissions, and then I echoed. Now notice I'm using a /bin here. That is historical. I don't think it's a problem these days, but there's an echo in the shell. And in older releases, if the values that echo wrote into the CPU's file, for example, was more than the CPU's allowed, maybe it's a 32 CPU system and I say go 1 to 32 when they're really 0 to 31, it's going to come back with a no space left on device. But if I'm using the normal built-in shell echo, I don't see the error. So by using bin echo, I can see an error if it occurs. So if I try to echo a CPU number that does not exist or a memory node that does not exist, it will say no space left on device. Also, I want to make sure that the mem I'm using is on the same node as the CPUs. I'm not going to grab the CPUs from one socket and tell them to use the memory on another socket. Another thing that's real bad, by the way, complained about it, I don't think the site ever changed it, but there was a site that created their boot CPU set across all nodes or all IRUs in the system. So they would have, like one blade out of each IRU or one socket out of each IRU to build their boot CPU set. That would be bad. I want them tightly coupled. Now that made sense in Itanium days, but not in UV days. I don't want to go across the interconnect. If I'm going across the interconnect and it's busy from contention from other things, I'm going to have problems. You want to tightly couple these CPU sets and try to keep them on the same blade, within the same IRU, and try to find socket blade IRU boundaries. So pick the right stuff there. Anyway, from there then I put my current shell into the task directory. I catted the task file to see I was in it. I can also cat $cpuset to see what cpuset I'm in. Also did a taskset to see my affinity. Now I cannot remove that cpuset if it's busy. So I CD'd out of there, and I might actually have a try to remove the directory, and it might complain that it's busy, not to go in and get the PIDs that are in the task file out of the task file and back into the global, and move all those all the PIDs into all their cpusets before I can remove it. Now the other thing, and this is a lab for you to do overnight or in the morning for you, probably easiest to do it right away, even while I'm talking. Go into your elilo.conf and in the append statement, add in an init equals sbin boot cpuset. By the way, if you're working with the React product, React uses cpusets, but it doesn't use a boot cpuset command. It has a react.pl script that it runs. And both of these things do the same thing. They create the cpusets before init starts to make sure that init, anything in init tab, or anything spawned up by the check config daemons are in that same cpuset. The other thing you have to do is define what's in the cpuset. Now this is hard-coded. You've got to use bootcpuset.conf. And in here I put the number of CPUs, the MEMS, and then I should say the CPU numbers I want to use, the nodes I want to use, and then I had a verbose statement. Also, I mentioned that this var run CPU node map can map things back and forth. And that's created by this on boot. Wrapping up here. The other thing I talked about were these spreads. So there's a boot cpuset memory spread loaded by SGI's Foundation software that sets these to a 1 by default. So if you've got Foundation loaded, this thing's happening. But I had an Oracle site. You need Foundation for the kernel modules. But I had an Oracle site that did not want spreads, so they check config this thing off to keep things first touch. And also I mentioned the memory pressure enabled. Lastly, bcfree, used to free files, pages from the buffer cache. Unfortunately, it will free everything. If I do a bcfree-a, even DSOs and shared text are lost, and then you're going to see them. We saw it the other day. Right after the bcfree, everything got reread back in, and I had a whole bunch of reads coming from disk to reload everything from disk that I just trimmed. And keep in mind, when I am reloading executables and DSOs, that gets counted as a page fault, a major page fault. Only frees non-dirty pages. There is an option on bcfree to do a sync command. There's an option available to flush per node, but when it does it per node, it's using memhog to do it. I'll also be using bcfree-f to trim the slab. And also I was using the drop caches. So the drop caches of 1, let me put it here. A 1 was the page cache, a 2 was the slab, and a 3 was both. Now we have to be a little bit careful here. There's also something called zone reclaim mode. This is what do I do and where do I trim when I have to trim, and that's broken right now. I have a special kernel, and I also have a special zone reclaim mode setting for this special kernel. If you were to grab this latest heady kernel that I'm running, check, and it should be a zone reclaim should be a 9, and it probably is not right now. So tomorrow when I get into this, I'm going to leave it as the default, prove that the zone reclaim, the node aware trim is not working right. It will allocate off node, and once the entire cpuset is allocated, then it will start trimming. And that's going to result in off node allocations and high latency and poor performance. We discovered that last December or so at a Mercedes site that was getting runtime variances. And I saw it last week at the University of Minnesota. So we need to get that node-aware trim working correctly. So I do have a new kernel there, and then a 9 for zone reclaim mode should get that node-aware trim working correctly. So I'm done. The labs. I don't care about TapSet, but play around with DPlace. I'm going to demo this tomorrow. Play around with DLook. Again, I need to get back into DLook summary. I'll show that tomorrow. DLook can get too verbose. DLook summary, I've got a line at the end that gives me the total number of pages on a node. And it's less verbose. I am really not doing any labs right now on OMPlace. So I am not concerned about you. You don't have to do this one. You don't have to do this one. But I do want you to get a bootcpuset configured. Also to get a login cpuset. I'll demonstrate that tomorrow. I've already installed PBS, and you're going to have to copy the PBS mom cpuset to PBS mom. And this is what I'm going to demo tomorrow. This is basically where I am. I only plan on working with NUMA Tools, cpusets, PBS, and running OpenMP and MPI in a PBS cpuset environment and trying to lock things down. So I plan on a demo tomorrow, reviewing NUMA, and then I got to talk memory, and that's about it. I still plan on pushing tomorrow, taking as much time as I can, but I still plan on probably going until 12:30 tomorrow.